So thank you, and I'd like to introduce Darko, and he is the CEO of CausaLens, and they do some really cool stuff, so I'll let him talk about what he does.
Thank you for that analogy with the dogs. I'll leave that in a minute. I'll be talking a lot about small data here, and it's exactly, what you said, that, people like to talk about big data and do this solve these sexy problems, but, forget how much more difficult it is to do machine learning on small data, and the probability of overfitting on that kind of data, exponentially kind of increases as the size of the data changes. So we'll talk a little bit about that, but before that, I wanted to ignore the long title for now. You'll know what it means by the end of it, but I just wanted to mention a few things about automated machine learning and why there is such a big fuss about this. This morning when I woke up, I didn't bake my own bread. I just went to the bakery and bought an amazing bread that I couldn't make myself. If I had spent maybe 3 or 4 hours this morning to make bread, I probably would have made better bread than bakery. But then I wouldn't be here talking to all these wonderful people and exchanging ideas. So I think strategically as humanity, we had to automate things in order to progress. I mean, everything we see around us is essentially a product of automation. It's about building automation on top of automation. So programming was a way to automate manual work. Then machine learning came along, it was a way to automate programming. And now the next step is automating the automation of automation. So automation of machine learning is about automation of automation of automation. And I don't think we'll be sitting here in 5 years' time and talking about, which is your favorite algorithm. I don't think that will be a question to be asked. Everyone will be talking about how they used one of the AutoML tools out there to solve a problem that had X ROI. How they improve the business, their sales, their marketing, whatever they were doing. I think that is what data scientists are going to talk about in the future. So now I'm going to talk about something very specific, which is time series data. So we're going to talk about automation of machine learning in the context of time series data. And so I just wanted to shed some light around what is time series and why is it special and where can we find it. So I come from the world of hedge funds. Majority of my team comes from that world as well. And we know very well how hard time series are, and the reason they're hard is because they have this. I can walk around, yes. They have this temporal element associated with them. When it comes to time series, you can know, the concept of time is such that it only goes forward. You cannot really turn time back. So you cannot do the usual tricks you can do in data science, where you can, do n-fold cross-validation, move the data around, stuff like that. So concept of time is key. Extracting time from data is half of the battle, if not all, when it comes to, predictions on time series. So here's some devices that generate time series data. You have the stock market. It's all about time series. You have, data servers. Anything in the Internet of Things is going to generate time series data. It's continuously kind of capturing things as they happen. Health data, smart transportation. Pretty much anything that changes over time. And as the economy gets more dynamic, we will see more of this data coming along. And so the reason we started CausaLens is because we felt that no one was able to do time series well. So we always had a lot of criticism when we looked at all the AutoML tools out there, how poorly they handle time series. And us coming from the some of the world's top hedge funds like Man Group, we have seen how to deal with these things, and we felt it was suboptimal. So anyway, that's what we're going to talk about, is how do we build predictive models on time series data. So now back to the small dog. it's very easy to build a good machine learning model if you have a lot of data. You know, you just throw it into deep learning. It's great. It works. Although, you know, in time series you might still you might still have problems with just throwing stuff to deep learning. But in the small data world, and especially on the non-stationary type of variables, like the one here, where we might have one data point per month or per week, doing machine learning is super hard. So first, small data. The second, this non-stationarity that you will observe a lot in financial markets. So non-stationarity more technically refers to the fact that the mean and variance of this signal varies over time. So what the world looked like in 2010 might be nothing like the world in 2016. So training a model that can adapt to this kind of changing underlying world is super hard. And then on the left here, what we have is, on my right, is the potential drivers that may impact this non-stationary time series here. And in the real world, we have data that looks like that. There's missing gaps, there are discontinuities, there is, again, some more non-stationary drivers. So if you just fed this into either AutoML or, pick your favorite thing, it's not going to work. It's going to, the way to make this work is to deal with an optimal way, of dealing with the missing data, optimal way of extracting time from it, and then choosing the appropriate algorithm, which might not be, all of our favorites deep learning things. But so what we're going to talk a little bit about here is going to be a bit scientific. We're going to talk about a solution to this problem, and we're going to talk about some experiments that we ran at a large scale this morning on the CausaLens platform to see the value of doing this, some of those highlighted steps here. So the talk is going to focus on solving this problem, and what we will know is, what I will say straight away is that neither end of the spectrum is going to help us with this problem. Econometrics lies on the kind of left-hand side, the least sophisticated type of modeling, and deep learning lies kind of here on the right, the most sophisticated type of modeling. And to solve this problem, we need to be somewhere in the middle. People have written, they have won Nobel Prizes on econometrics. They've written books. When we try it on real-world signals, they don't do so well. Deep learning, again, people think is the panacea, it's the silver bullet. When you try it on this kind of data, it doesn't deliver. So first, I'll talk about the human and the machine. So why are humans still have a role to play into this? By the way, this is my experiment setup. We're going to only change one thing at a time. We will run a plethora of algorithms. We're going to run kind of anything that is out there. Facebook's profit, gradient boosting, random forest, the whole thing. We're going to run it across many data sets from different worlds, from finance, from retail, from transportation. And we're going to compute a bunch of metrics, to understand whether, our experiment works or not. So we're going to test some hypotheses. Let's see. Human and machine. First, before I show you what these graphs mean, I want to give you a practical example from one of our customers. We were given a couple of hundred time series, to feed into the CausaLens platform to build an optimal predictive model. So we did that. We threw a lot of machinery at it. We did some really clever stuff, and we got some reasonable predictive model. It was on this small data problem. Then the customer came back and said, you know what, our kind of business user or, has some insights about the world that he would like to incorporate into the modeling process. What that meant was, to narrow down from a couple of hundred potential inputs, to 10 or 20 that the person felt would be the most important drivers into this modeling process. And so when we repeated the fully autonomous way versus the kind of human selected, reduced sample set, we were able to see, really improved performance. And then we ran this at a much broader scale, this experiment, and you can see the results. On the left is the mean absolute error. The blue is with the full inputs in a fully automated way, and the orange is when a human has selected inputs. And you can see across all of these different data sets, the error goes down when a human has, an expert. It's not any human. It's someone that really fundamentally understands the problem that they're trying to predict. So this is your business user. So this is kind of a case that we cannot have data science teams that sit in some lab locked away. We need to bring this technology right in the hands of the guys that actually, make the money at the end of the day. On the right is just another metrics that proves essentially the same point there. By the way, the Pearson R here refers in all of these things as the correlation coefficients between the ground truth and prediction. So perfect result is 1. So second step is feature extraction, and this is super important in the world of time series. So this refers to the notion of extracting time from data. If you just feed the values directly into an algorithm, you get very suboptimal results, and you can see it here super clearly. You have complexity 0 refers to just feeding essentially the values straight into a model. Complexity 1 refers to extracting time from time series, like things like momentum, mean reversion, things that mean something. You can do those things manually, by the way. Of course, you can do it manually. It's just, the iterating through manually extracted features, can take a long time. And when we come to the full pipeline, this will become even more apparent. It's kind of exponentially growing space. So far, we did two things. We saw the value of human. We saw the value of extracting time from time series. The second bit we'll see is the value of reducing that dimensionality. I'm sure you're all aware of the curse of dimensionality. More data doesn't result usually in better performance. What it usually results is this known concept of overfitting. We might get an amazing thing to show to our stakeholders, but the thing is not going to work, and we're going to damage our reputation and the reputation of the team. So, reducing the dimensionality of the data is paramount. So this just kind of illustrates it, through example by running it across, a plethora of different algorithms and a plethora of different data sets. And here we have data sets from finance, we have from retail and from transport and some health data as well. So kind of the whole spectrum. By the way, a lot of these things are time series specific. You might not have the same results if you're doing image things. So, my PhD is in computer vision, and I recently met my professor, a world leader in this area, and he said, Darko, we forgot about feature extraction now. We just throw it all into deep learning. It's magic. It's great. But unfortunately, in the time series world on small data, that doesn't work so well. Now, when you put all of those steps that we described earlier into a holistic pipeline, what do I mean by that? How do you do those things all together? How do you optimally impute and clean the data? How do you extract the right features? How do you select the right features? How do you choose the right algorithm? And how do you choose the right parameters of the algorithm? And how do you then automatically score the models, the hundreds of thousands of models that you evaluate in a way that you don't overfit for the future? You get an optimization space that looks like that. It's discontinuous in its nature, and it's very large in dimension. So you cannot traverse this space. You cannot optimize with your usual kind of gradient descent type of approaches. There's no gradient that exists between a neural network and a gradient boosting, let alone between an algorithm and how do you impute the data. So we have a lot of IP around how do we optimize across this space, and some people call this derivative-free optimization. So we have trained a specific optimizer that can find the right model out of hundreds of thousands for you in there. And that's really hard, by the way, to do. It takes a lot of experiment. And you can see kind of here the value of actually doing that. So if you did each step individually, and you spend even a month or two, you'll get, the results with, the worst results across data sets. If you do it in a clever way, if you optimize, we use, a bunch of stuff, including Bayesian optimization, and a bunch of other things. Can't really reveal too much about that part because that's kind of the secret sauce. But you really get empirically here is the value of doing that. Now, the last thing, I might show you something if we have time. But before we do that, I want to draw the attention to how else you can deal with this small data problem. So what we do is we've built some really cool algorithms which automatically generate artificial data that is very much like the data that you're trying to build a predictive model on. So we have a service where you can throw some data, and in return you get more of the data that is very similar to the one you put. So you can actually use it as a way to both, in our case, train this super clever optimizer, this gradient-free optimizer, but also to produce more data to train your models on. So that's yet another way to deal with this. And we've seen, I don't need to read this, but essentially we've seen the power of synthetic data, and how we can essentially learn much faster than a human can ever learn if we generate data with known properties that are very, very similar to the real world data. So what I want to show you actually now, before I show you that, I want to show you how this problem that we talked about would look like if it was in Excel, essentially. So this is just so you can visualize it as a kind of a little summary. This is kind of the problem we were just solving in those steps. We have a variable x that we are trying to predict, and we have a bunch of potential drivers, for that variable. And you can see in real-world data we have various frequencies, we have lots of missing gaps, we have all sorts of stuff. So our machine essentially can take this and come up with a full solution, a full model, which will include how to clean the data and all these other steps that we discuss in the presentation. So before I wrap up for questions, just wanted to give you a sense of a few things about us. We are a London-based startup. We hire kind of the brightest and the best data scientists in the field. Myself and my co-founder come from kind of a scientific background, PhD in physics, PhD in AI. We have worked for some of the world's most prominent hedge funds and research institutions. We are going to be a team of 9 soon. We are also hiring, by the way, but let's not compete too much for talent. And we're backed by some prominent, London-based VCs. So on that note, I don't want to bore everyone with, and I don't want to turn this into marketing pitch, so I'm not going to do the actual demo, but you can imagine it is essentially one line of code that will take that CSV file and give you a production-ready solution that you can just fit within your workflows wherever you need it. So on that note, I would love to take a few questions, and maybe we can have a little debate.
So how do your results compare against, say, ARIMA models with the appropriate seasonality corrections and regime change kind of corrections and unit root removals and all of that? So did you guys do that?
Sure. So we actually use a ARIMA model. So I just said on this particular problem they don't do so well out of the box, but we have them on kind of the one side of the spectrum. and we automatically essentially embed corrections for seasonality. So we have what it's called known in advance variables, which is kind of like day of the week and the month and holidays that automatically get embedded into it. Then we perform all of our analysis on stationary time series, so you can be confident about the error metrics. We feed the non-stationary and stationary components. So we do it. I think it works very well in some cases. I mean, the question is, what works on each problem. So my comment was just on that particular problem, but otherwise, nothing fundamentally wrong with the RIMA model. Oh yeah, why not? Actually, we have someone that is trying it out for crypto.
So how much do you help interpret your results? Like, you come up with a model Y, but it looks like you also impute a lot of these variables, right? So say, for example, you use mean imputation versus a median imputation, and that helped the prediction. Like, do you explain it to us, saying that, hey, I actually did a mean imputation, worked better, and
absolutely, yeah. That's actually the kind of the fundamental value we bring, is that we want full transparency around the whole process. So when you get the model, you get or you're comparing models, you'll get exactly the imputation method that was applied on each time series, and you can actually explain that.
Do you do any Fourier extractions?
You can do that, yeah, of course.
Is it AutoML, and does it say, hey, when I did a Fourier imputation and used this particular frequency component?
Absolutely, we've done that. Yeah. That's if you like, part of our API. So it's not part of the user interface. People don't necessarily understand Fourier transforms and conversions into the frequency domain. But if you are a savvy user and you're using our API, you can absolutely do that. And I like Fourier a lot, so I try it a lot of the time. Yes, so we have our customers are asset managers, hedge funds, banks, transportation companies. So this is used to manage billions of dollars on a daily basis.
What kind of illuminated input does it apart from the data? What method
So in theory, no other input will be required, although it's all about asking the right question. So you might want to know whether a particular variable is a driver of something, in which case you might want to build two models, one which has that variable, one which doesn't have. In that case, that's your human input. You say, this is my hypothesis, and I'm going to test it using this machine. Really, we just have a machine that builds models, but you can ask so many questions, and this is where we think the human really comes into the play.
Does your application sit on top of one of those, or do you build your own, or are you using something else?
Yeah, so we would love going forward to partner with some of those guys that are specific, they specifically store time series data and be part of their toolbox. But for now, we just use standard approaches on that kind of open source. So we're not really on the storage of data. Like, we don't have any edge there, and that's not our business. But of course, to do this, you have to store the data somewhere. So we provide that on our, but we use cloud infrastructure which already has those data sets. I'm aware of specific time series data sets that exist on there.
Next question: how do you deal with the challenge of, I don't know if you call it upsampling or downsampling, where I have some, in our business we have things that maybe don't change, for months, and then it'll change a bunch, and then it'll go back into a dormant state where it doesn't change very much. And so from a data storage perspective, I only want to store a row every time the data changes, but then how do you analyze that?
Sure.
Do you upsample it, or?
Sure. So we, we would probably classify it as a categorical variable. So we would potentially model it as such. In terms of upsampling and downsampling, it's done on the fly automatically. So you don't actually have to store perfectly aligned time series, and that's kind of part of the first step of the optimization. How do you automatically align data which is not aligned? So, you could give us data that is not, does not contain any data in between. We will automatically figure out how to do that.
Great product, right? So do you also monitor the performance of these auto-build models? So you monitor it, and do they auto-correct itself for your previous accuracy, for example?
Yeah, that's a great question, and this is kind of where our technology shines. We are aware that the world changes, painfully aware, coming from the finance world. So we have a bunch of online models that we run, and you can build notifications in which you say, hey, this model no longer, simplistically you can say, once the residuals between the ground truth and the prediction start expanding, please let me know. And then choose the next, best model that works in this new world. And you can only do that if you can efficiently build models automatically. In the current world, where actually human data scientists have to go and rebuild the models from scratch, that becomes harder to do. In an automated fashion, when you could look at 100 models for one variable if you want, and you can have an ensemble of them. You can look at how they, what is the standard deviation between their predictions. I mean, you really can go wild. It's about opening new ways of doing things. It's about opening, doing things that you were not able to do before. Before we had no airplanes. I couldn't just hop to Dallas from London to talk to you guys. I had to take a boat and travel for 3 months. But because there's a plane, I can come here. It's the same in data science. Because we can do it automatically, we can do more of it.
This is a follow-up to Vishwanath's question. In addition to wavelet transforms and statistics from sliding windows, do you use other feature transform techniques?
So we do have some standard things like Fouriers and wavelets, but we haven't really gone wild on that side just because our customers wouldn't understand what they meant. Now, if you wanted to do that, you could. I mean, it would be just, if you wanted to do some fancy things, it would be just another line of code before the optimization where you can just transform your CSV, into something that you care about, or just add a few more columns of your favorite feature transformation, and you can see how they perform. So you could do it. It's just we don't do it automatically to preserve the explainability and stuff. But.
Is there a penalty? Let's say you already did something. Instead of showing profits, the market has gone in a different way, and it gave losses to your customers.
Mm-hmm.
So how does that impact the software prediction and the reality? Is there a penalty on the software company if you do that?
Well, we don't build predictive models. We give the machine to people to build it for themselves. So they're the ones that stand behind the model, not us.
So this is just a follow-up to Vinny's question. So how important is it for your customers that this is not a black box? So you give them this tool, and if it gives the results, and it gives the results consistently, do they really care?
Great question, and I think you have two schools of thought there, and depends really on who you speak to. The most common answer we've heard is that first, let's have an explainable model. Let's have a model that we understand, kind of, sort of. At least it's kind of has the right inputs that are in my Excel file. And let's use that as a baseline. Then let's throw a lot more machinery at the problem, and let's see how much better the new model will be. If we get a model that significantly outperforms the baseline, people tend to be happy to use it, or at least to have it there running and just observing. But if it's a marginal improvement and it's unexplainable, then it's hard to justify having an unexplainable model. And you have lots of other model risks that you're running by doing that.
So I want to go back to what you had said about AlphaGo and artificial data gathering. You were talking about how that's sort of on the cutting edge of that field or whatever. And I'm just wondering, like, what kinds of innovations have been made in terms of that data gathering?
Sure.
That makes it so cutting edge now versus like bootstrapping which has been around for 50, 60 years?
Well, I think there's two innovations. One is how do you build automatically, or how do you generate synthetic data that is like real data? So it's about measuring features in real data and then producing, using those features to train a model that produces, data that is very similar to what may happen in the future. So that's one innovation. The second, I guess, is just doing it in the right experimental setup. It's about creating an experiment. In our case, it's about traversing this exponentially growing discontinuous space. So it's more about, it's not necessarily about, the innovation that, oh, hey, we have artificial data, now we can do clever things. It's about where do you use the artificial data. In our case, we use it on a specific use cases. Is how do we train a machine to always come up with the best possible predictive model on time series. So the innovation is in applying it into a use case in which it hasn't been applied. And as I said, the other innovation is in generating data that is as close as possible to reality or what might happen in the future. Does that answer it? Sort of. We talk later more. I think I'm out of time, I think, officially. But I'll be around. We can chat more.
Thank you, Darko. That was very interesting. So now everybody knows the scientific definition of small and big data. And I appreciate you talking about the dogs. It makes it more fun. So one thing that I just wanted to share is we're going to take a coffee break, but there's some really great sponsors here. And I want to make sure you guys meet Anna and Jeremy at Formulated By, because they're the ones